Have you ever wondered what sound is and how it works? Well, we're about to embark on a fascinating journey into the intriguing world of sound. Sound is an inseparable part of our lives. It's in the gentle rustling of leaves, the melodious chirping of birds, the loud honking of cars, and even in the silence of a quiet night. But what really is sound? At its core, sound is a type of energy, but not just any energy. It's energy that's created by vibrations. Yes, you heard that right. Every sound you hear, from the lowest of rumbles to the highest of pitches, is caused by something vibrating. When an object vibrates, it causes the air particles around it to move. These particles then bump into the particles next to them, which then bump into the particles next to them, and so on. This chain reaction is what propels the sound energy through the air, and voila, we have sound. But let's dig a little deeper. When we think about sound, we often think about something we can hear. But sound in its most basic form is just energy. It's like a hidden force that's constantly moving around us, interacting with the world in ways we can't even see. Imagine for a moment a world without sound. It would be like living in a painting, wouldn't it? The colors, the shapes, the movements would all be there, but it would lack the depth and vibrancy that sound brings. Sound gives our world dimension. It's more than just something we hear, it's something we feel, it's something we experience. Whether it's the soothing sound of rain falling on a tin roof, or the jarring sound of a car alarm in the middle of the night, sound has the power to evoke emotions, to tell stories, and to create experiences. So the next time you listen to your favorite song, or hear the laughter of a loved one, remember what you're really hearing is energy. Energy that started as a vibration and traveled through the air to reach your ears. Sound, as we perceive it, is only the tip of the iceberg. At the heart of what we call sound are vibrations. But what are these vibrations? Well, let's delve into it. Vibrations are essentially rapid back and forth movements of particles. Picture a stone landing in a still pond. The stone's impact sends ripples across the water's surface. Those ripples are like the vibrational waves of sound spreading out from the source. Now what happens when an object vibrates in the air? That object, let's say a ringing bell, moves the air particles around it. It's like the bell is giving a little push to the air particles next to it. And those air particles, they don't keep the energy to themselves. No, they pass that energy on to their neighbors, and those to their neighbors, and so on. This creates a chain reaction, a wave of motion that radiates out from the bell. These waves, moving through the air, are what we call sound waves. They're invisible to the naked eye, but they're powerful enough to travel great distances, carrying the sound of the ringing bell with them. But here's the thing. Sound doesn't just travel through air, it can move through any form of matter, be it a solid, liquid, or gas. That's because all matter, regardless of its state, is made up of particles that can vibrate and pass on these vibrations. Ever noticed how sounds are louder when you're underwater? That's because water particles are closer together than air particles, meaning they can transmit the sound waves more efficiently. The same principle applies to solids, where particles are even more closely packed. So in essence, sound is a form of energy that comes from vibrations. These vibrations create waves that move through the medium around them, whether it's air, water, or a solid object. And these waves, when they reach our ears, are interpreted as sound. To sum it all up, when we're talking about sound, we're really talking about vibrations. The strum of a guitar, the crash of thunder, the murmur of a whisper. Each one is a different kind of vibration moving through the air, reaching your ears, and being interpreted by your brain as sound. Vibrations then are the very essence of what we call sound. These vibrations in the air reach our ears, but how do we actually hear them? It's a fascinating process that starts when these sound vibrations or sound waves make contact with our ears. But let's not get ahead of ourselves. Our ears are not just simple funnels for sound. They're incredibly sophisticated pieces of biological machinery designed for capturing, amplifying, and interpreting these vibrations. The outer part of our ear, the one you can see and touch, is called the pinna. Its unique shape helps collect and funnel sound waves down the ear canal. And at the end of this canal lies a thin, sensitive membrane known as the eardrum. The eardrum is so sensitive that even the slightest vibration can make it move. So, when the sound waves reach the eardrum, they cause it to vibrate. These vibrations are then transferred to 3 tiny bones in the middle ear called the ossicles. These bones are the smallest in the human body, but they play a massive role in our hearing. They amplify the vibrations from the eardrum and pass them into the inner ear, or the cochlea. The cochlea is a snail-shaped fluid-filled organ lined with thousands of tiny hair cells. As the vibrations enter the cochlea, they create waves in the fluid. These waves bend the hair cells, and as they bend, they generate electrical signals. Now here's where things get really interesting. These electrical signals are then sent along the auditory nerve to the brain. Our brain is the ultimate sound decoder. It takes these signals and transforms them into something we recognize as sound. Whether it's the melodious notes of your favorite song, the soothing sound of rain, or the voice of a loved one, it's your brain that makes sense of it all. So the next time you're listening to your favorite tune or enjoying the sounds of nature, remember this incredible journey that sound takes from the source to your perception. The process of hearing is a remarkable journey from vibrations to conscious perception. Ever noticed how you see lightning before you hear thunder? That's because sound has a speed. Sound, like light, travels in waves. But unlike the lightning-fast pace of light, sound takes its time, cruising at a relatively leisurely speed. In dry air at room temperature, sound waves zip along at approximately 762 miles per hour. That's around 13 times slower than the speed of light. So, when a thunderstorm brews, we see the flash of lightning well before the rumble of thunder reaches our ears. But it's not just about air. One of the fascinating things about sound is that its speed can vary depending on the medium it's traveling through. In general, sound waves move faster through solid objects than they do through liquids, and faster through liquids than through gases. That's because molecules in a solid are packed together more tightly than in a liquid or a gas, allowing sound waves to transfer energy more quickly from one molecule to the next. Now let's talk about the concept of the sonic boom. Ever heard a jet breaking the sound barrier? That loud boom you hear is a sonic boom. When an object moves faster than the speed of sound, it's said to be supersonic. As it breaks the sound barrier, it essentially outruns its own sound waves, creating a shock wave that we hear as a sonic boom. It's like sound's version of a firework display, a grand announcement that it's arrived. So, the next time you're watching a thunderstorm or a jet streaks across the sky, take a moment to appreciate the speed of sound. It's not as swift as light, but it has its own unique rhythm and pace. And it's this speed that shapes our perception of the world around us, influencing everything from the music we listen to the way we communicate. Sound might not be the fastest traveler, but it certainly knows how to make an entrance. Ever wondered why a violin sounds different from a drum, even when they play the same note? Well, the answer lies in the magical world of frequency and pitch, two crucial aspects that shape the way we perceive sound. Let's start with frequency. Frequency, measured in hertz, is the number of vibrations, or cycles, a sound wave completes in 1 second. Imagine you're at a pond and you toss a stone into the water. The ripples that spread out, those are like the vibrations of sound. The more ripples in a given time, the higher the frequency. Now let's connect this to sound. When an object vibrates quickly, it creates a high-frequency sound wave. This results in a high-pitched sound, like the squeal of a mouse or the high notes on a piano. On the other hand, if an object vibrates slowly, it creates a low-frequency sound wave, resulting in a low-pitched sound, like the rumble of thunder or the deep notes of a bass guitar. But here's the twist: the frequency alone does not define the character of a sound. That's where pitch comes in. Pitch is our auditory perception of frequency. It's how high or low we perceive the sound to be. While frequency is a measurable fact, pitch is subjective. It's how our ears interpret those frequencies. So, back to our initial question, why does a violin sound different from a drum, even when they play the same note? It's because of the unique combination of frequencies each instrument produces, known as the harmonic series. Even though the violin and drum might be playing the same fundamental frequency, the balance of additional frequencies or overtones they produce gives them their distinct sounds. So the next time you listen to your favorite tune, remember it's all a game of vibrations and frequencies. The beauty of music, the thrill of a scary sound, the comfort in a familiar voice. They're all down to how these vibrations are played out in the grand orchestra of life.